All right, so to finish up section 3.9, we're going to look at how to solve inequalities involving fractions. So we have to look at fractions a little differently because of restrictions that are introduced due to the denominator. So in order to do this, let's think about when a fraction, it's going to start the same way. So with an inequality, let's think about it in terms of when does this whole thing equal 0? And then, so we'll first start thinking about when it equals 0, and we'll still use that test point method, but we have to take into account the restrictions from the denominator as well. The good thing about a fraction is the fraction equals 0, so no matter what we have down here, I'll just use the same example from part 1. This equals 0 anytime the numerator equals 0. So to start, which would be the first step of finding the zeros of this whole side of the inequality, we really just care about when that numerator equals 0, because then the whole fraction would equal 0. So just like with the problems we saw in class on the first part of this lesson, we always need to factor first. So once we factor, then we can find our zeros. So before I continue and looking for my zeros, I'm going to factor this entire fraction. So the numerator factors, I want to figure out what's multiplying to negative 12 and adds to negative 1. And that would be negative 4 times positive 3 is negative 12, negative 4 plus 3 is negative 1. So my numerator is now x minus 4 times x plus 3. And the denominator, x squared minus x. So I can just factor an x out of that. X times x minus 1. So let's first start looking at, I want to know when that whole thing is greater than 0, but again, just like the strategy we saw in class, let's find the actual zeros first. So what are the zeros? When does this whole thing equal 0? And that would be when the numerator, the zeros are 4 and negative 3, because anytime the numerator equals 0 would be my zeros of this entire function. Now, the step that is added to this, because we're looking at a rational function, is that we also need to consider the restrictions on x. So I need the zeros, and this step 1 up here says find the zeros of both the numerator and the denominator. I have the zeros of the numerator. The zeros of the denominator are basically what x can't equal, because I have to remove those from my domain when I plot my points on the number line to use the test point method. So x cannot be 0 or 1, and that's coming from this denominator. So now when I plot my zeros on the number line to use the test point method, I must plot the zeros of the function and the restrictions. So display all of them. So I'm going to put my smallest one is negative 3. I have 0. And 1 and 4. So with all of those zeros, I have to test 1, 2, 3, 4, 5 intervals. So testing these points is where it gets challenging to stay organized, just keeping track of all the values we're thinking about. So I'm going to pick a number less than negative 3. Again, it can be, I pick super, super negative. So I'm thinking a very negative number times another very negative number. So I'm plugging it right back into this inequality and checking to see if it's greater than 0 or not. So I'm checking to see if it's greater. I'm going to have a negative number plugged into this times a very negative number plugged into this. That's going to be a negative times a negative. So that's going to result in a positive in the numerator divided by a super negative number times a super negative number, which would multiply to a positive again. So then in this interval, I've got what ends up being positive divided by a positive. So that is going to be a positive value. Okay, next I need to test a point in between negative 3 and negative 1, or sorry, negative 3 and 0, so I'll pick negative 1. So when I subtract 4 from negative 1, negative 1 minus 4, that's going to be a negative, but when I add 3 to negative 1, that's positive. So it's going to be a negative times a positive divided by x, so negative 1 times x minus 1, so a negative times a negative. So a negative times a negative. So I'm going to simplify that here. So my numerator is a negative times a positive, which is negative. And then I'm dividing that by negative times a negative, which is positive. So this is what I mean by saying there's a lot to keep track of. We have to keep track of what every single factor would be when I plug in this negative 1. So again, it would be a negative number times a positive number. So total negative numerator divided by a negative number times a negative number, which is positive. So a negative divided by a positive will result in the end in a negative number. So now I need to pick something between 0 and 1, so I'm thinking about the value of 1/2. When I subtract 4 from 1/2 right here, that's negative. When I add 3 to 1/2, it's positive. So the product in the numerator would be negative times positive, which is a negative, divided by whatever we have in the denominator, 1/2, so x itself, 1/2 minus 1, so that would be a positive times a negative. So that would also be negative. So my result, negative divided by negative, is positive. Now something between 1 and 4, so I'll pick 2. When I subtract 4 from 2, that's negative, but when I add 3, it's positive. So the product is negative. And then in the denominator, I would have 2 times 2 minus 1, so both of those are positive, and their product would be positive. So then overall, I have a negative number divided by a positive number, and gives me a negative result on the interval 1 to 4. And then finally, something larger than 4. So again, with these extreme values, I pick something really, really, really large. Because no matter what happens, if I pick like a super, super large positive number, subtract 4, add 3, it's still going to be super large. So that numerator is a positive times positive, which results in a positive. Denominator, also large positive number, minus 1, still a large positive number, which multiplies to a positive, and then that is also a positive interval. Okay, so we've tested points and found out that this function is positive. So think of this number line as the x-axis. It's above the x-axis, then in between negative 3 and 0 it's below, and then it's above, and then it's below, and then it's above. So I'm checking specifically for when this function is greater than 0. So I cannot include any of these zeros. We'll never be able to include zeros from the denominator because it simply cannot equal those values. So these two would always be open circles no matter what. But since we're looking for strictly greater than, then these are all open circles. So again, my solution is coming from where this is positive, and we see it being positive on these intervals. So how do I write my solution? I would write that in interval notation. And I'm out of room. So I will write it down here, and then I'll have to erase it. So my solution for this is negative infinity to negative 3, union 0 to 1, union 4 to infinity. So just a quick recap. You need the zeros from the numerator because that's when a fraction equals 0, but we have to include these restrictions on our test point method as well. So we had to include 0 and 1 because since the function can't equal 0 or 1, there is a sign change on either side of both 0 and 1. Okay, so moving on, let's look at number 6. Okay, so with number 6, again, I'm checking in the end to see when this whole function is less than or equal to 0. I need to first think about the zeros of this rational expression, which would be when the numerator equals 0. This needs factored. So again, the first thing I'm going to do is factor. If you look at the numerator and denominator, these are both differences of squares. X squared minus 1, x squared minus 4. So the numerator factors to x plus 1 times x minus 1. And the denominator, x squared minus 4, factors to x plus 2, x minus 2. When is that whole thing greater than or equal to 0. So let's first check and see when this whole thing equals 0. So I need to find my zeros. My zeros are when the numerator equals 0. So that would be when x equals -1 or +1. Next, I need to look at my restrictions, my values that x can never equal no matter what, because I have to make sure I test points around those boundaries as well. So x cannot equal positive or -2. Once I have all of my zeros and my restrictions, then I place those on a number line and use the test point method. So -2, -1, 0, whoops, I don't need 0 on there. I just need +1 and +2. So now I need to pick values in between each of those and test them. All right, again, it's important to stay organized. So I keep track of signs below my number line and then put the final result above it. So I'm going to plug in a number that's less than -2. Super, super, super negative number. When you add 1 or subtract 1 from that very negative number, it's still negative. So it will end up being a negative times a negative, which results in a positive numerator. In the denominator, again, add 2 to a very negative number. Subtract 2 from a very negative number. You're going to have a negative times a negative still, which is positive, and then their quotient will be positive. All right, so here's where it gets tricky with testing in between these three very small intervals. So between -2 and -1, so think about -1.5. When you add 1 to -1.5, that's still negative. So I'm going to keep track of all of these. Negative times -1.5 minus 1, which is also a negative. Divide that by -1.5 plus 2, that's going to be positive, and then I subtract 2, and it will be negative. So right now I'm showing this kind of in-between step. So I'll have a negative times negative numerator, which results in a positive, and then a positive times negative, which results in a negative. So this interval, positive over negative, will have a negative result. Now between -1 and 1, when you can pick 0, pick 0. So if I pick 0, it would be +1 times -1, so a negative numerator, and then again +2 positive minus 2 negative, so a negative denominator as well, but the quotient overall, a negative over negative, is a positive interval. Next, between 1 and 2. So I'm going to pick 1.5, so think carefully about 1.5. Adding 1, clearly still positive. Subtracting 1 from 1.5, 1.5 minus 1 is still positive. So you would have a positive times a positive, which is positive. In the denominator, 1.5 plus 2, positive. 1.5 minus 2, negative. So you would have a positive times a negative, which is negative. Now the overall quotient, positive divided by negative, is negative. Last, we test something very, very positive, way larger than 2. Add 1, subtract 1, you're still at a positive value. And then add 2 and subtract 2 from this very, very large positive number, you still have a positive. So this final interval is positive. Okay, so let's see, we were checking to see when this was greater or less than or equal to. So let's think about that. The zeros themselves, this is the tricky part. The zeros themselves, -1 and 1, it can equal 0. So at -1 and 1, I'm putting closed circles because that's where our function equals 0, and I'm solving for when this function is less than or equal to 0. So I can include those in my intervals. However, the restrictions 2 and -2 are values that are not in our domain. So even though we're checking for when it's less than or equal to, we can never include these values because the function is not defined there. So this is interesting because I have some filled in circles and some open circles. My solution for when x is less than 0 is right here. So negative there and negative there. So looking at those those boundary points, -2 to 1, I'll have a parenthesis at -2 for my solution. So the solution is -2, -1, but the -1 will have a bracket because I can include that value. And then a union and +1 with a bracket because it's filled in, but 2 with a parenthesis. So this is my solution. So this means the function is negative here, it crosses positive, negative, positive. Okay, so we've got one final example left. I would like you to try this on your own. So I would hope that at this point you would pause the video. I'm going to work through it so that you can check your work. But I would really like to see if you can do this on your own. I think it would be good for you to know where you are as well in your level of understanding. So go ahead and pause the video, and then you can just fast forward to the end and check your work. And if it's not correct, you might want to just go back through and watch how I arrive at the answer. So this problem, to find the solution for when this rational expression is greater than or equal to 0. Again, I'm going to start by factoring. So my numerator factors just by taking the x out. So that would be x times 2x plus 5 over x minus 4, and we're checking to see when that's greater than or equal to 0. The denominator does not need factored. So first I'm just going to look for my zeros from the numerator, which would be 0, and when I set 2x plus 5 equal to 0, that 0 would give me -5 halves. Also, I need to consider my restriction of 4. So I have my zeros and I have my restriction. So -5 halves, 0, and 4. So those are the 4 intervals that I need to test. So my first interval here, anything less than -5 halves. -5 halves is -2.5. So just think super, super negative. I'm going to have a negative times a negative in the numerator. That's going to result in a positive. And then, positive divided by a super negative number and subtract 4, and it's still negative. So that would be a positive divided by a negative, which is negative. Next, I'm going to pick something between -2.5 and 0. So I'll just pick -1. So -1 itself, negative, 2x plus 5. So that's 2 times -1, which is -2, plus 5, which is a positive number. So this would be a negative times positive. So a negative overall in the numerator. And again, I chose -1. And when I subtract 4 from that, it would be negative. So a negative numerator, negative denominator, and that results in a positive interval. Next, I'm looking at a number between 0 and 4, so I'll think of 2. That would be 2 itself, positive, times 2 plus 5, also positive. So that's a positive value divided by 2 minus 4, that would be negative. And positive over negative, so that's an overall negative interval. And then something much larger, much more positive than 4. It would end up being a positive times a positive, which is positive, divided by x minus 4, which would still be positive. Okay, so I was looking for when this was greater than or equal to 0. So I can include my 0 since it was greater than or equal to. So I can include 0, so that would be a filled-in circle, and I can include a -5 halves. However, my restriction on x of 4 has to remain an open circle. And then I was checking for my solution, which would be greater than or equal to. So these intervals are my solution. So that would be with brackets, -5 halves to 0, bracket union, parenthesis 4 to infinity. So hopefully you were able to follow along with these examples, and that wraps up 3.9, and I'll see you soon.